in this video, we're going to talk about how you can approach floor function integrals. And by the end, you should have a decent understanding about the methodology and the strategy used to solve some of these problems. So let's get started. First of all, what is the floor function? Well, the floor function of x is defined to be the largest integer that is less than or equal to x. So for example, if we were to take the floor function of 2.5, the largest integer that's going to be less than 2.5 is going to be 2. Say I wanted to do the floor function of pi, the largest integer would be 3, as pi is approximately like 3.14. Say that the floor function of 105.8 is just going to be 105. So that's just what all the floor function is. Now, why is this a problem when we're integrating? Well, let's sketch the floor function on a graph. So I'm going to go between 0 to 4. Now, between 0 and 1, the largest integer is just going to be 0. So it's just a straight line at 0, between 0 and 1. But suddenly when we're at 1, between 1 and 2, the largest integer that's less than or equal to some number between 1 and 2 is going to be 1. So you have another straight line between 1 and 2, the height of 1. Similarly, between 2 and 3, our line's just going to be 2. And then between 3 and 4, we're just going to have 3. So you'll notice that since there's so many discontinuities with this function, it's not very nice to work with when we're doing an integral. So how do we go about that? Well, what you can exploit is the fact that this function is constant in every integer interval. So for example, between 0 and 1, the floor function is a constant number. Between 1 and 2, the floor function is a constant number, and so on. So let's look at an integral and see how this comes together. So we're going to look at the integral between 0 and infinity of 4 to the minus floor of x dx. So, as I was saying, if we were to break this integral down into the integral between 0 and 1 plus the integral between 1 and 2 plus the integral between 2 and 3 and so on infinitely many times, then we can use the fact that floor of x is a constant in each of these integrals and then sum the integrals together, and then we'll have our answer. So what do I mean? If we were to actually write out one of these integrals, so let's say we have integral between 0 and infinity of 4 to the minus floor x dx. We can write that as the integral between 0 and 1, and then the floor function of x when x is between 0 and 1, as we said, was just 0. Similarly, between 1 and 2, the floor function of x is 1. And then between 2 and 3, the floor function of x is 2. And you can see that we're just going to repeat this infinite many times. So we will write this integral as an infinite series of integrals that are only one integer wide. So you can write this as the infinite sum from k equals 0 to infinity of the integral between k and k plus 1, and then the floor function is just going to be k, that lower bound. Now we notice that 4 to the minus k is just a constant with respect to x. So we can take that out of the integral. Now we just have the series k equals 0 to infinity, 4 to the minus k. And now we just have the integral between k and k plus 1 of 1 dx. And evaluating that integral is just 1 as well. So really, this isn't even an integral. It's just a series from k equals from k equals 0 to infinity, 4 to the minus k. So typically with questions, as long as you're comfortable with working with series, you should be okay in solving floor function integrals, because that's really all they are. So if I were to actually evaluate this series, you notice that this is actually a geometric series with the common ratio of a quarter. So you can say this is 1 over 1 minus a quarter. Then we get our answer as 4 over 3. So that's just that integral done like that. So to recap what we did, we want to consider the floor function of x as just some constant number between all of these integer intervals. So by writing this integral between 0 and infinity as an infinite sum of integrals between one integer and the next integer, then we don't have to worry about the fact that the floor function is discontinuous absolutely everywhere, because it's just a constant in each of these integrals. So let's move on to a slightly trickier example. We have the integral between 1 and infinity of 1 divided by the floor function of x times x squared dx. So we can use the exact same idea as before, where if you split this integral between 1 and 2 plus 2 and 3 and so on, then the floor function of x is just a constant value that we don't have to worry about. So once again, we can say that this integral is the infinite series from k equals 1 to infinity of the integral between k and k plus 1, so one integer and the next integer, and the floor function of x is just going to be k. And then we'll keep x squared as it is, because that is still a continuous thing. So now this is what we're working with. Okay, so let's work this out. We can take out that 1 over k from the integral, and then we'll just be left with the integral between k and k plus 1, and I said I was taking out the k, of 1 over x squared dx. So let's just focus on that integral for now. Integral between k and k plus 1 of 1 over x squared dx is just going to be minus 1 over x evaluated at k and k plus 1, which is going to be minus 1 over k plus 1 and then plus 1 over k. So if we were to put this together, we have sum from k equals 1 to infinity of 1 over k, and then we've evaluated that integral as 1 over k minus 1 over k plus 1. Alright, so now we have this series to work out. K equals 1 to infinity, 1 over k squared minus 1 over k lots of k plus 1. Okay, so let's evaluate this series. So if we break this up into two series, we have the one of just 1 over k squared, and then the 1 over k lots of k plus 1. Let's focus on this left series for now. Now this series on the left is actually just the Basel problem, and it's got a very famous result as pi squared over 6. So that's just something to keep in mind. So we have pi squared over 6, now we have an actual sum that we want to do, k equals 1 to infinity of 1 over k lots of k plus 1. So to solve this series, we're going to perform partial fraction decomposition. So we can say that 1 over k lots of k plus 1 can be written as something over k plus something over k plus 1. And then in doing so, we get 1 here and minus 1 here. Okay. The sum from k equals 1 to infinity. Now we want to work out 1 over k minus 1 over k plus 1. So let's consider this as some finite sum first. So say k equals 1 to n. Now if we were to actually write this out, we could write this as 1 over 1 minus 1 over 2. And then when k is 2, we have plus 1 over 2 minus 1 over 3, and then plus 1 over 3 minus 1 over 4, and so on. And then our last term is going to be plus 1 over n minus 1 over n plus 1. So you can see that every time we have a minus, we just have a plus of that same thing right after that. So these all cancel out. And then, as I said, there's a plus right after the minus. So this one cancels out. So this series is just the same as 1 minus 1 over n plus 1. So let's say we instead wanted to consider when this goes to infinity, we can just take the limit as n approaches infinity of this sum. And when n approaches infinity, 1 over n plus 1 will approach 0. So this sum is just going to be 1. So all in all, our answer is just going to be pi squared over 6 minus 1. And that's it. That's our integral done. So yeah, that's just the general idea that you want to do every time you have a floor function integral. We just want to split that integral up into integer-wide intervals, so we end up with some infinite series of integer-wide integrals. So we can treat that floor function as a constant, and then compute the rest of the integral as if it was normal, and then compute the series. So let's do one more. This one is slightly different. So the integral between 0 and infinity of minus, and this is a different function. This is called the fractional part function of x to the power of floor x. So what is the fractional part function? Well, similar to how if we were to take the floor of 3.14, that's going to be 3, but the fractional part of 3.14, as the name suggests, is going to be 0.14. So another way that you can think about the fractional part of x is just going to be x minus the floor of x. And that's exactly what we're going to do in this integral. So if we were to once again break this down into an infinite series of integer-wide integrals, so you have the series from k equals 0 to infinity, and then our integral between k and k plus 1, we're going to have minus the fractional part of x, and the floor of x is just going to be k dx. Now, as I was saying earlier, in this bottom line here, the fractional part of x is just x minus the floor of x, and here the floor of x is just k. So let's write that. Integral between k and k plus 1. So inside of this we have minus x minus k, and that's to the power of k dx. So we want to do this integral. First we can take out this minus sign that's inside of this bracket here, and take it outside of the integral as a whole, since it has nothing to do with x. So we have minus 1 to the power of k, and then our integral between k and k plus 1 of x minus k to the power of k dx. And we can just do a substitution for x minus k. So say u equals x minus k, we get du equals dx, and now we end up having integral between, then k minus k is just going to be 0, and k plus 1 minus k is going to be 1. Then we just have u to the k du. So if we were to evaluate that integral, we'll just get 1 over k plus 1. So really, what we have is the infinite series of minus 1 to the k over k plus 1. And something you might notice is if we consider the series expansion of ln 1 plus x, this is actually just this series here when x equals 1. So we can say that this series is just the natural log of 1 plus 1, which is the natural log of 2. And that's just our answer, and that's what we have to do. So hopefully you have a decent understanding of how you can approach these problems now. Genuinely, the main idea is just splitting up that integral into a series of integer-wide integrals. So you can treat the floor function as a constant and do everything else as normal. So I hope you found this video helpful. Let me know if you have any further questions, and I'll be happy to answer them. Thanks.